into the board. What's the magnetic field here in the front? Down. What's the magnetic field behind at the, up? But over here, this is the magnetic field everywhere around, so it would be along the circumference. Actually, if you want to introduce like theta, like that, right, then it would be in the direction of, instead of saying circumferential, you can say theta hat. In the direction the theta increases in polar coordinates. Like the electric field is away, so r hat in the direction of the unit vector r hat, the magnetic field is in the direction of theta hat. So this is, what you will be doing is going to be this. That's Ampere's law. For very long straight wires, you can just go straight to this line. Right? So the length of the Amperian loop is always going to be a circle with the wire along the axis of the circle. And then the circumference of that is 2 pi r. And then equals mu naught I. And then, so you can write this, 1, 2, and this is given. And then this is already the answer. Right? So if there is one expression that you should know for the magnetic field generated by whatever, it would be the magnetic field generated by a very, very, very long straight wire with constant current I in it at a distance r away from it. Mu naught I over 2 pi r. Mu naught I over 2 pi r, like kq over r squared, or 1 over pi epsilon naught q over r squared. So mu naught I over 2 pi r.
This might not be relevant to the class, but I was wondering if all magnetic fields are like loops, how come two magnets can like attract one another? I'm trying to think about. Is that?
What that means is that you cannot have, so let me answer your question like this. Suppose you have a bar magnet. So this is a bar magnet. I don't know, maybe made of iron. It's made up of atoms, iron atoms, right? And suppose I put a strong magnetic field, an external. I create the magnetic field, and I grab this bar magnet, and I put it in this strong magnetic field, and suppose the magnetic field, the external magnetic field is this way, and it goes right through it. So this is an external magnetic field. What will happen is that the atoms that make up this bar magnet, the iron atoms, it's like they're all going to talk to one another and interact with one another, so they all face in the same direction. So they are going to face in the direction of the magnetic field. What's interesting about it is that if you then, this is like, imagine authorities come and they stand outside and they say with a loudspeaker, everyone in the Lewis building, face towards the parking lot. And then, you go like, oh, okay, then I'm going to face that way. And then you turn and you face that way, and then you face that way. We all face that way. And same thing with the people in the next room, and in the next room, and over there, and people in the bathroom, and downstairs, we all face that way. We're all lined up. Right? Now, what's interesting is that in this case, you can remove that external magnetic field, like get rid of it. And they stay like that. They remain like that. That's what makes them permanent. So they stay like that. Now, you could say that, therefore, the magnetic field comes out over here. They seem to be coming back in here, right? Well, not quite. Yes and no. Yeah, they do come out over here and they do come back over here. Come back. Because what happens is that this magnetic field line goes right through, but it goes around. And so the end of the magnet, it turns out that the Earth, let me address that question further, because we have to talk about that anyway. Nickel does the same thing. Cobalt does the same thing. Those are three metals that at room temperature can be magnetized and stay magnetized when you remove the external magnetic field that was used to magnetize them. Now, if you grab two magnets, for example, what's observed is this. Suppose this is magnet number 1, and this is number 2. This one has, let's say, a magnetic field coming out like this. And let's say this one has, let's make it the same. By the way, these are called magnetic field lines. These things that I'm drawing, the use of those lines is to tell me the direction of the magnetic field at any point. Like over here, the magnetic field is tangent to that line. Over here, the magnetic field is tangent to it. Right? Over here, the magnetic field is this way. Over here, the magnetic field is this way. Right? Same thing with electric fields. Now, if you have these two magnets interact with one another, they end up attracting. In other words, this magnet feels a pull this way, a magnetic force, and this one feels a pull this way. So let's call this, how about, this is where the magnetic field goes out, and this is where the magnetic field goes in, out, in. So if a side of a magnet has a magnetic field going out, it attracts the side of a magnet where the magnetic field is going in for the other magnet. This is just nature, that's the way it is. Right? Now, hold on, we have other cases. This is number 2, and this is number 1, right? So what happens if we have them like this? Now this, I have them like this, so I'm gonna have them the other way around. And same thing over here, right? Well, what happens over here? They're going in, they're going out. In, out, the magnetic field lines. These two also attract. So this one feels a force this way, and this one feels a force this way. You know, they pull on each other. One more possibility, or two more, but it's sort of the same thing, same result. Let's say this is magnet number 1, and this is magnet number 2. And let me draw the magnetic field coming out over here. So it goes like this. But over here, it also comes out. Okay? So here, the magnetic field comes out. Here, the magnetic field comes out of that magnet. Here it goes in, and here it goes in. Well, it turns out that out with out, near each other, repel. So this one feels a force this way, and this one feels a force this way. They repel. Okay? And you can imagine the other one. In I can, there's one other possibility, right? Number 1, number 2. So this was going in, this one is going in. So what do we have now? The magnetic field lines at this end go in, and over here they also go in. Well, they repel. So you could call the ends of a magnet in and out. Go ahead.
I was just gonna say, does it work like that because once they're together and like attracted and?
I'm getting there.
Oh, okay.
Now, it turns out that, can I erase this? We don't really need this anymore, right? It turns out that the most beautiful planet in the universe, which one is that?
Earth.
Of course. It's the only one I know too, right? So this is planet Earth, right? This is where Santa lives. Antarctica. The Earth has a magnetic field. And the Earth has a magnetic field as if it doesn't, but as if with the same profile outside of it, as if it has a bar magnet stuck inside of it. It doesn't have a bar magnet stuck inside, but magnetic field, right, is like this. As if you had a bar magnet, and the magnetic field of the Earth, I'll use a different color, comes out of here, wraps around planet Earth, and goes back in. Actually, you know, but it actually goes right through because, you know, it forms closed loops. So this is out of the magnet, right? I mean, you also have magnetic field lines that go like this, but I don't care about those because, you know, we never go there, right? But outside, you have something like this. Now, suppose you take one of these bar magnets, right? And the end where the magnetic field comes out, you paint it. I don't know, you paint it green. And now you take this magnet and you're over here. Let's say out at sea, in the middle of, you know, well, of the sea, of the ocean, right? And you take this magnet, your magnet, right? Now that magnet interacts with the Earth magnet. Now, which end of this magnet is going to point towards this end?
The out.
The one where it goes out, right? Because the out attracts in. So then my magnet is going to point like this. With this end, maybe I should have drawn it black. I'm exaggerating the size of this, right? So this is my magnet. So where actually the in would be down at the bottom, right? You know, just to use that. So that means that my magnet, since this is a magnetic field going in, right? In attracts where the magnetic field comes out. So that means that my magnet is actually going to be like this. Now, from my perspective, which way is this end of the magnet pointing? Where Santa lives, right? It points north. So instead of calling it in, out, which is making me hungry, out of in and out, instead of calling it in, out, people then call this end the north end, because it points towards the north, because of its interaction with the Earth magnetic field. which happens to be coming out at the bottom. And then the other end of the magnet is called the south end. So electric charges, you call them plus minus. The ends of a permanent magnet, you don't call them plus or minus, you call them north and south. Because when you let that magnet interact with the Earth magnetic field, one end is going to point towards the north, what we humans call north, and then we just call that north. And the other end we call it south. So, but what that means is that so where the magnetic field lines go in, that goes with south, right? And where the magnetic fields come out, that goes with north. So that means that for the Earth magnet, this is in, this is south. And this one will be north. So one has to now be more careful, because we call this the North Pole. That's where Santa lives, right? Otherwise the Polar Express wouldn't make any sense. But we have to be more explicit now when we say the North or the South Pole. This is the North geographic pole, and this is the South magnetic pole. This is the North magnetic pole of the Earth, but this is the South geographic pole of the Earth. So north goes with south, south goes with north. They're opposite. Now, suppose you have a magnet like this, and I call this north and this south. That's how they label them. Instead of plus minus, they label them NS, north, south. Right? I know that the magnetic field comes out the North Pole, right, of the magnet. It goes like this and goes like that. Now, and actually it goes right through like this, right? Now, suppose I decide to break this magnet in half, and I go like this. I cut it. Do I just have a magnet with just a north magnetic pole and a magnet with just a south magnetic pole? The answer is no, because what's going to happen is that this line is going to come out like this, and then it's going to go like that. And this one is going to go like that, it's going to go like that, right? And this one is going to come out over here, but then it's going to go back over there. Because you don't have this anymore, because you changed what you had. So you still have a place where the magnetic field comes out, which is the north end, right? And this is the south end, and this is the north end, and this is the south end. And to answer your question, what happens if you put these two together? Now it's like going backwards. You put these two together, right? And what will happen is that this magnetic field line is going to join this one, and then you just have one like that, and then you just go back to just having one north and one south. So now you know why they're called north and south magnetic poles, because the pole of the magnet that points towards the north is actually interacting with the Earth magnetic field, right? Which has a pattern around it, a profile around the Earth, as if it had a south magnetic pole over here. But we don't look at this one, we look at that one. Oh, it points north, and so, that's towards the North Pole. Yes. Now, the interesting thing about this, remember how we got this magnetized? What did we do? We just had this chunk of iron. We put in a strong magnetic field. And then you remove that external influence, that magnetic field, and the atoms stay lined up because of the interactions between them. Some of the magnetic properties are related to the free electrons that go around the metal. Other magnetic properties are due to the core electrons, the ones that remain, not the ones that leave. Other magnetic properties are due to the nuclei of the atoms that interact in a certain way that line up sometimes they line up this way, ferromagnetism this way, anti-ferromagnetism. So anyway, you have various possibilities, and if you have a bar magnet like this, for example, and it actually goes right through. See, people say, oh, magnetic fields start at the North Pole and they end at the South Pole. No, they come out at the North Pole, they wrap around, come back at the South Pole, but go through the magnet from south to north. So if somebody asks you, what is the direction of the magnetic field? Is it from north to south or south to pole? Well, then your answer should be, it depends. Do you want me to tell you the direction of the magnetic field outside the magnet or inside the magnet? Because inside the magnet is from south to north, but outside the magnet is from north to south. Yes? So people think of, oh, they end over here and they begin over there. No, they don't. That's where they come out, but they go back into the unit, and then right through the magnet, the magnetic fields continue. They don't really end over there. I mean, if you didn't have any magnetic field lines over here, then you could say, yeah, they come out over here and then they end over there. But no, they go through. So they don't really start or end there. Okay. And we can, that expression that I just gave you, the one that we derive with Ampere's law. What if you have this? What if you have this? Suppose you have a very long wire, and the current is to the right. Let's say the current is 5 amps to the right. And there's another very long wire that's parallel to it. And the current is to the left, I2, 5 amps. And suppose the separation between these is 8 meters. So 2 very long parallel wires. And I want to know what is the magnetic field that these wires generate right between them. So let's be right there. Where this is 4 meters, and this is 4 meters. What do you think is the answer? What is it? Okay, that turns out to be the wrong answer. I put enough symmetry in here that may lead you to think that the answer is 0. But why not? Why is the answer not 0? So this is like another example. This is an application of knowing the magnetic field generated by 1. Remember, we used Gauss's law to derive the electric field generated by 1 point charge? 1 point charge plus Q. Electric field, right? R, so we did a Gaussian surface. E times 4 pi r squared equals Q over epsilon naught. This is E equals 1 over 4 pi epsilon naught. Q over r squared, or KQ over r squared, right? So you can use Gauss's law to derive that expression. Now, when you were given a problem with 2 point charges, let's say one here and another one there, right? Some distance A, maybe A. And the question was, what's the electric field over here? Did you use Gauss's law to do that? If you had 2 point charges, did you use Gauss's law? No. What did you use? If this is plus, you said it generates an electric field pointing away from it. If this is minus, you said it generates an electric field pointing towards it. And then you added the 2 vectors. So you use this result for each point charge, right? Found the magnitudes and directions of the electric field there, and then you invoke the superposition principle, and then you added the vectors. So it's the same thing over here, right? We already know what the magnetic field is generated by one of these, using Ampere's law, we were able to derive it, mu naught I over 2 pi r. But if I have 2 or 3 of these wires, I don't use Ampere's law necessarily anymore. I can just use the result of this one. So the magnetic field at the center over there would be the magnetic field generated by the current in wire number 1 plus the magnetic field generated by the current in wire number 2. Now, what is the magnetic field here generated by the current in wire number 1? Let's say this is wire number 1 and this is wire. So, what is the magnetic field generated over there by the current in wire number 1? So, what is the expression that you need to know for very long straight wires?
B.
So, what should I write down for the first one?
5 mu naught over 2.
So it will be mu naught times, let me write it as I1 over 2 pi R1, right? Where R1 is going to be this. And I'm going to call this R2. Now, which way is that magnetic field pointing generated by the current in wire number 1?
Into the board.
Into the board, right? Plus the magnetic field there generated by the current in the other wire down below, which is mu naught I2 over 2 pi R2. Now, which way is that pointing? My finger's going to the board at the top. This point is above wire number 2, but this point is below wire number 1. So this is also into. Yes? Right? Let's go back to this picture here. If the current is that way, put my thumb that way, at the top, the magnetic field is out. But the wire at the top, the point that I'm looking at, here's wire number 1. So I'm looking at the bottom. This point is at the bottom. So for the wire number 1, which is at the top with the current that way, I'm looking at this point. Right? And then there, the magnetic field is into the board. But for wire number 2, this point is above it. Right? So now let's say this is wire number 2, but now the current is that way, and the point of interest is above. Put my thumb this way. At the top, my fingers are going into the board. Yes?
It's kind of probably a bad time to ask, but how do we know which way for?
Put your thumb of your right hand in the direction of the current.
There we go.
Of the current in the long straight wire, and the fingers will curl around in the direction of the magnetic field.
Okay, thank you.
So notice, these two vectors are not going to cancel out. Everything else is the same about them, right? They have the same magnitude of current, they have the same distance. I did that deliberately. But those two vectors are not going to cancel out. They're two vectors that point in the same direction. So this will be, mu naught is 4 pi times 10 to the minus 7. I1 is 5. And then I have 2 pi, and what is R1? 4 meters. And this is into the board. Plus, the other one is 4 pi times 10 to the minus 7. I also made the current 5 amps. And this is 2 pi, and R2 for the other one is also 4 meters. And this is also into the board, right? So notice that this 4 pi cancels those 4 pi, and this 4 pi cancels those 4 pi. So we have what? 5 divided by 2 is 2.5 times 10 to the minus 7 into the board, plus 5 divided by 2 is 2.5 times 10 to the minus 7 into the board. So you get, how do you add two vectors that point in the same direction? This would be 5 times 10 to the minus 7 amps. Sorry, what are the units of magnetic field? Tesla into the board. Okay? So once you know the expression for the magnetic field generated by one long straight wire, if you have multiple wires, it's just like, just find the magnetic field through each wire and add up all the vectors. Questions?
So if the currents are going the same direction, they would cancel one another?
They will cancel out because like for this one, my fingers are going into the board at the bottom, but for this one, my fingers will be going out of the board, same magnitude, the magnetic field will be zero. Exactly. That's right. Now, a picture that is worth observing for a long time until you know it. So, when you go to bed tonight, you know what you should do, right? A picture that you should really, really, really look at for a long time is this one. This picture. Here's the wire with current going that way. The blue circles represent the magnetic field lines. Magnetic field is tangent to those circles. Right? Notice, the current is to the right, so the magnetic field curls this way. So notice that at the top, it's tangent to the right. At the bottom, it's tangent to the left, if you're looking at it like this. Over here is tangent going down, and the back is tangent going up. Everywhere on this cut over here, the magnetic field is going out, 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 out. The dots mean out, out, out. And on this plane over here, magnetic fields are going into, so those are X's. So the X's mean into, the dots mean out. But that's a picture that you should really look at, and so what's given is the wire in yellow. You have to imagine these rings going around it with the magnetic field curling around the wire. What if we have a very long wire, and now we're interested in, it's a wire that's got a thickness to it, so the radius is A, it's straight, and the current is I naught, the total current, distributed uniformly. I didn't say that over there, but it's distributed uniformly. So, this is example number 2. I mean, it's number 3, but I think B, right? So what we have here is a wire like this. Right? It's very long, infinitely long. The radius of it is A. And the total current in the wire, uniformly distributed, is I sub 0. And there are 2 regions of interest over here. Right? So, I sub 0 is distributed over this area, right? So wire continues, right? So there are 2 regions of interest. I want to know what is the magnetic field inside this wire. And what is the magnetic field outside the wire? So, inside, that's when R is less than A, right? So that would be like right here. Suppose I want to know what is the magnetic field right there at a distance R. So what is the Amperian loop that I imagine for very long straight wires like this? A ring passing through that point. So that's my Amperian loop. All right, so this is Ampere's law. Good. So, with the Amperian loop that I just imagined, right? It's a circle, so it'll be B times the length of that circle. Should it be 2 pi A or 2 pi R? What should I write down?
2 pi r.
Right, because it is the length of the Amperian loop, which has radius R. And this equals mu naught. Now, I enclosed is the current that goes through this loop. And that's going to be less than I sub 0, because I sub 0 is distributed over the whole cross-section area. So how do I figure out I enclosed? And this is uniformly distributed. So how do I enclosed is less than I sub 0, correct? It's some fraction of it. So how do I figure out I enclosed? Because that's what I need to put in here. So what goes in here? Any ideas? Uniformly distributed is a hint. Yes? Any ideas?
2 pi r over 2 pi a times I.
But the current is not distributed over a length.
It's distributed everywhere.
It's through an area. This current is distributed through this area. What's the area of this circle here?
I see. Pi a squared.
Right, and what is the area of that?
Pi r squared.
So what should I write down? So, but you have the right idea. I can say that I enclosed is to the area over which is distributed, as I naught is to the area over which is distributed. This is actually, this one has a name. The total current, through the wire divided by the area over which is going through is the current per unit area. This is called current density. We call it J. But you will just call it like that. So I enclosed is I naught over pi a squared, that's the current density, times pi r squared. So that is what we need over here. And notice that this pi cancels that pi. So I get that the magnetic field is going to be mu naught I. Notice that one of these r's cancels, well, that r cancels one of those r's. And here I have 2 pi a squared. Yes? What about outside the wire? That's when any r greater than the radius of the wire, right? So that would be like if I want to know the magnetic field here at a distance r, which is greater than a, right? So what do? I imagine an Amperian loop like this, passing through that point, so that the wire is going down the center, right? So this is my, I'm going to call it AL. Amperian loop. So I write down Ampere's law, B dot dl equals mu naught I enclosed. And in these cases, it's B times the length of that Amperian loop, which is 2 pi what?
R.
R. And what is the total current that goes through that Amperian loop? What's the total current going through this Amperian loop?
I naught.
It's just the current through this, right? Which is I naught. So notice that once you step outside the wire, the magnetic field is the same as if all the current were through the center. Or not through the center, on the axis. So now if I draw a graph, if I sketch a graph of the magnitude of the magnetic field as a function of distance, right? Any value of R over here is inside the wire. And everywhere over here, we're outside the wire. Well, this is the expression for the magnetic field inside. So as a function of distance R, what is this? A circle, a parabola, a hyperbola, what's up? What is this? I'm putting this on the y-axis, and I'm putting this on the x-axis. This is y equals mu naught I or 2 pi a squared x. What is that an equation of? It's a line with positive or negative slope.
Positive.
And what is the y-intercept?
0.
0. So it's just a line. Now, as soon as you step outside, the magnetic field goes as 1 over r. So what should that look like?
Exponentially downward.
But not quite an exponential, but yeah, but like that, right? So I will do other geometries next time. We're gonna definitely finish this on Wednesday, for sure. So I'm just gonna go over the remaining examples. I'm gonna go over the coaxial cable. Coaxial cable is simple, well, relatively simple. And then I'm gonna go over what's called a toroid, which is, as you'll see, simple. And then a very long solenoid. I'll just do those 3 relatively quickly. I'll do them in detail on Wednesday. So therefore, your exam number 2 should be next Wednesday. This way you have, I'm gonna for sure finish this on, this Wednesday, and then next Monday, we can review, you can ask me questions, blah, 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 right? And then next Thursday, I keep saying Thursday, Wednesday, and this is going to be on chapters, I think the first example was 21, 22, 23, right?
Yes.
So this will be 24 through 28. Well,
Excluding 27.
excluding 27. And it's easier to just write down the numbers than to write down excluding. So 24, 25, 26, and 28. 4 chapters, not bad.
Well,
So I'm going to put up, one of those chapters has to do with capacitors. I'm going to put a problem with a circuit with capacitors. Another chapter had to do with resistors and batteries. I'll put another circuit problem with, where you have to use Kirchhoff's laws, right? Which, and then a couple of problems on magnetic fields. One of them where you have to do an integral, but the simplest type, not as complicated as the one that we did today. And then an ampere slope problem, which these guys you do in 2 minutes.
Will we have a RC circuit problem at all?
What's that?
Will we have like a resistor capacitor circuit problem at all?
No,
Okay.
they tend to be, yeah. That's the lab that I like to do this week, the RC circuit. I was gonna do another one with diodes, but maybe I'll do that one later on, so that this one will be, well, not quicker, but
So it's not gonna be a problem specifically on chapter 25. Just like 25 doesn't really,
25 kind of.
it doesn't really cover anything you can question on.
it introduces definitions of
Just like
current and,
incorporated, yeah.
yeah, it's a plug and chug, like if this is, then the formulas are given to you and so. But you need that to build up and better understand 26. 26 is when you have the circuits, right? So, yeah. So I'll see some of you later today, right? If you came in late, let me know so I mark you present. And the rest of you have a nice evening.